now let's talk about laminar and turbulent flow. So, basically we are focusing on velocity boundary layer. So we have seen this in fluid dynamics in great detail, but I'm going to briefly summarize it just as a reminder. So again, let's say we have a fluid at a incoming stream velocity u infinity, and if we send this fluid about a plate, we are going to have a boundary layer developed. The boundary layer initially will be smooth and it will be laminar, and as you go further down to the stream, so you are going to have a transition region and then you are going to have a turbulent region. Okay, so the laminar region will have velocity streamlines. They will be almost one-dimensional, and in boundary and in the transition and turbulent region, we have a lot of mixing and we have a lot of motion in x and y direction. Okay, in the laminar region, the dominant motion is in x direction, although you may have a weak motion in y direction. But in turbulent flow, all of the motion in x and y direction are equally important. And the criteria for the transition from laminar to turbulent flow is Reynolds number, and the critical Reynolds number is 5 times 10 to the 5. Again, this number is different when you are dealing with a flow inside a pipe. This criteria is for the transition for a flow across a flat plate. Okay, so this is the criteria for the transition from laminar to turbulent flow. Okay, and if you actually plot the thickness of the boundary layer, let's say this is the fluid that comes across this flat plate, the thickness of the boundary layer will gradually increase in the laminar flow, and then increase will be much more in the turbulent flow. Okay, so if on the other hand, if you take a look at the H value, the local heat transfer coefficient, so along the laminar flow, H value is actually decreasing, and then in the transition region you have a sudden increase, and then there will be a decrease again. So now I would like you to pause here and think about why do you think that we have this non-monotonic trend for H. Okay, so now let's think about this. So for this region, for the laminar region, so we have the definition of local heat transfer coefficient. So Ts and T infinity are constant. Kf is constant, so we have dt by dy to calculate the local H value. So as you can see, if the thickness of the boundary layer is increasing, so that means dt will be mostly the same, but dy will be increasing. So that means this term, as you go from leading edge to the right direction, this term is going to be more and more. It will be larger and larger. So that means this term, this derivative will be smaller and smaller. So that's why you have a decreasing trend in here. So regarding this increase in here, so we must think about the bulk motion of the fluid. So we not only have the fluids that are mostly going in x direction, but now we have fluid molecules that are going in y direction. So that means that the fluid molecules here, let's say at cold temperature, and fluid molecules are in here high temperature, they will collide with each other because there will be net motion in y direction. So they are going to collide and they are going to transfer energy to one another. So that means they are going to increase the heat transfer through mixing effect. And because of that, because we are introducing a strong motion in y direction, that enhances the mixing, and that's why H will increase. And then afterwards, you will be reaching the turbulent layer. In this case, as in the previous case, so the thickness, the mixing effects are more or less the same. So you always have now the motion in y direction. All of these striations, all of these fluid molecules in this region will have a strong mixing in y direction. Now, again, this term, this thickness is increasing. That means this delta y is increasing. So this means this derivative is decreasing. So that's why you have a decreasing trend again. Okay, so these are the reasons behind this complex looking behavior here. So this is again a very simple example. So it is just a algebraic example. So in this example, we are interested. So we are trying to find the condition to basically. So we are trying. Okay. In this example, we have a plate, and we would like to know what is the minimum length of this plate to reach a Reynolds number of 10 to the 8. Okay, so and this is in wind tunnel, so we are using air as the fluid. So the velocity of the air is given, temperature of the air is given. So the temperature will influence our properties, density, viscosity, Cp, so on and so forth. So we need to look up these properties at this particular temperature. And then the first question is, what should be the length to reach this Reynolds number for the plate? And question B is, at what distance the critical Reynolds number is achieved? So again, this is very straightforward problem. I'm just going to write this down, so without going through the simplifications. So we want to write down the definition of the Reynolds number, rho times u infinity times x over mu, or if you, okay, let's say rho times Reynolds number is rho times u infinity times x over mu, or if you like to write it down in terms of the kinematic viscosity, u infinity over x over kinematic viscosity. So we want to know what is the x to achieve a Reynolds number of 1 times 10 to the 8. So we rearrange this equation. X is equal to Reynolds number times kinematic viscosity over u infinity. So Reynolds number is 1 times 10 to the 8. And we look up the kinematic viscosity for air at 25 degrees Celsius. And we'll see that this is 15.7 times 10 to the minus 6 meter square per second. 15.7 10 to the minus 6. And then the velocity is 50 meter square per second. So we'll find that the distance is 31.4 meter. So that is part A. And part B is, what is the length to achieve at what position the transition happens. So the same story, in this case we'll be calculating x critical. So that means we need to evaluate it, we need to use Reynolds number critical to find x critical. And x critical is basically 5 times 10 to the, so Reynolds number critical is 5 times 10 to the 5. And kinematic viscosity is the same, velocity is the same, so that means 0.16 meter. So that means the transition happens within 0.16 meter, and the total length required to reach a Reynolds number of 10 to the 8 is 31 meter. Okay, again, this was a very simple algebraic example, just to illustrate the utility of the equation here.